In this video, we will start from digital circuits and practice optimizing them to minimally sized digital circuits. Here in this sample circuit, we have 4 logic gates and 2 inputs, A and B. So what we can do when optimizing digital circuits is we can create a system of equations. Let's label these output nodes. Here, we'll call this F. We'll call this output node of this logic gate G, and the output node of this logic gate H. This will give us a system of equations. F is equal to, we have a NOR gate here, A or B, quantity prime, so A NOR B. G is the AND operation of A and B. So G equals A ANDed with B. Now we have here a NOR operation. We have F NORed with A. H equals A NORed with F here. A or F quantity prime. Finally, K is equal to G or H. And we have a preliminary system of equations. What is K equal to? So let's solve for K in terms of A and B. K equals G here, so let's substitute for G. A ANDed with B, and then we OR that with H, which is A NOR F. Finally, we can substitute for F here. K equals A ANDed with B, or A or A NORed with B. And then we have the prime again. And now we have an equation for K in terms of A and B that is unoptimized. So how do we optimize? We can use De Morgan's law to solve this larger term here. So K equals A and B, and we have A prime ANDed with A or B quantity double prime. This double prime cancels, so we have K equals A and B ORed with A prime ANDed with A or B. And now we can use the distributive property. K equals A ANDed with B, ORed with A prime A, ORed with A prime B. So we can immediately see that A ANDed with A prime simplifies to 0. And then we have K equals A ANDed with B, ORed with A prime B. Factor out the B by the distributive property, and we get B ANDed with A or A prime. And we see that this is equal to 1. So K is equal to B. So our simplification here, we can actually remove all 4 of these gates. So 2 possible implementations. We have B, K as an alias, or we can say B and then we use a buffer. This is the symbol for a non-inverting logic gate, identity gate. So in a digital circuit, the buffer can be used to change a variable name if necessary, and it has some meaning, electrically speaking, when you use transistor circuits and implementation. But that's beyond the scope of this discussion. So let's look at the truth table. If we have inputs A, B, K, we have 4 possible input combinations because we have inputs 0, 0, 0, 1, 1, 0, and 1, 1. K is equal to B, so when B is 0, K is 0. When B is 1, K is 1. When B is 0, K is 0. And when B is 1, K is 1. We do not care what the value of A is here. It doesn't matter. And we have our simplified logic circuit and a simplified truth table. Let's look at a slightly more complicated scenario. Here we have 3 input variables, though we have only 2 logic gates. Let's try simplifying here. We have this output from a logic gate, which is B, or actually, let's give it a name first. We'll call it F, and this is equal to B ANDed with C prime. So we can solve for J, which equals A and B and F, which is equal to A and B and B, C quantity prime. Let's use De Morgan's law on this quantity here, and we get A ANDed with B, and we have B prime or C prime. Because we distribute this prime here, it changes AND to OR, and we have B prime here ORed with C prime. Now we can use the distributive property. A, B, B prime ORed with A, B, C prime. This drops to 0 because B ANDed with B prime is 0. And so J equals A, B, C prime. Let's draw our truth table. How many input variables we have? We have A, B, C, so we have 3 input variables. And our output variable is J. How many combinations do we have? We have 8, because 2 to the power of 3 is 8. So let's list them all. So 4 zeros and 4 ones for A, 2 zeros, 2 ones, 2 zeros, 2 ones for B, and then alternating 0, 1, 0, 1 ad nauseum for C. And we have all our input combinations. Note that J is only equal to this one term here where A is equal to 1, B is equal to 1, and C is equal to 0. If A is equal to 0, then J is equal to 0. So we can already zero out these 4. If B is equal to 0, then J is going to be equal to 0 again. So we'll single those out. Notice that if C is equal to 0, then C prime is equal to 1. 1 ANDed with something, it could be whatever A and B is. But if C is equal to 1, then C prime is equal to 0. So we can say if C is 1, J is equal to 0. Because 0 ANDed with anything is 0. So the only case where J is equal to 1 is this entry here. And this is our final truth table. In conclusion, we have our minimized digital circuit. We can draw an AND gate and an inverter here, like so. So we have A, B, and C, and then we have our output J. Our final digital circuit that we will optimize is listed here. So here we have 5 logic gates, and let's list them out here. We'll call this here, because it's on the output of an inverter, we'll just call this B prime. And the output of this inverter we will call A prime. Let's now call this output here F, and this output from this NAND gate G. And so we have our output I here. So F is equal to A and B prime quantity prime. Let's delete this prime here. It's not F prime, but F is equal to A, B prime quantity prime. And G is equal to A prime B quantity prime, like so. Finally, I is equal to F and G and C quantity primed. So we have a NAND gate again. So let's solve here. How do we solve? Well, let's use De Morgan's law first on I, and we will get F prime or G prime or C prime. Now we can substitute for F, which is equal to A, B prime, quantity prime, double prime. Let's substitute for G. A prime B primed double prime, ORed with C prime. We can cancel out the double inversions, so we get A B prime or A prime B or C prime here. Now we have this quantity here. This is equal to A XOR B. So we can say here I is equal to A XOR B or C prime. Now, let's try doing this. Let's say Q equals A XOR B, and we can say I equals Q or C prime. We can use De Morgan's law again to simplify further and say I equals Q prime ANDed with C prime. Note that we get I equal to A XOR B quantity prime ANDed with C quantity prime. Now, why use De Morgan's law here? Because this is an equivalence gate. So I equals A equivalence or XNOR B ANDed with C, quantity prime. Because the inversion is on the outside of the AND operation, we can use a NAND gate. So we can say A XNOR B, and we can NAND that with C. This gives us our output, output I. So we have a 2 logic gate solution. What does our truth table look like? Well, we have 3 inputs here. So let's write them out. We have A, B, C, output I. And so our table has 8 entries. Let's list them all. 0, 0, 0, 4 zeros and 4 ones for A, 4 zeros and 4 ones for B, alternating by 2s, and then alternating 0, 1, 0, 1 for C. So if A and B are the same, and C is equal to 1, then I equals 0. So A and B are the same here, and C is equal to 1. So I is equal to 0. A and B are the same here, and C is equal to 0. C is equal to 0 here, or equal to 1 here. So we have a 0 here. So notice that because A and B are not the same here, we have a 1. So 0 ANDed with anything is 0, but then inverted is equal to 1 through the NAND gate. It's the same here. So 1, 1, 1. And if C is equal to 0, 0 ANDed with anything is 0. Inverted is 1 again. So I equals 1 here and here. And this gives us our final truth table for our digital circuit.